Okay, so yesterday we looked at period integrals. We had a period integral I, which was the integral of some regular algebraic differential form over some chain. So omega was a regular n form on X, smooth algebraic variety over K, subfield of C. Sigma is a chain of dimension n. And it was allowed to have a boundary which is contained in some algebraic subvariety of codimension 1, the divisor. Okay, and then from this data, we formally defined some kind of symbol. But of course, this rests on some quite deep theorems in algebraic geometry. And the Motivic version of this integral was what I call the matrix coefficient. And here Hn xy was a triple in some category. So it consisted of relative de Rham cohomology, which is a finite dimensional vector space over K, consisting of all such possible closed forms in some sense. Betti cohomology, which is the dual of relative homology of X relative to Y. And there was a comparison isomorphism, C, which, or I call it P, I think, which gives the data of the integration pairing. And this triple lived in some category I called curly H. As we discussed, there's quite a lot of flexibility in what you can take for H. You can jazz this up with extra structures. That can be quite a useful thing to do. In any case, the basic idea is always the same. So this thing, IM, is an element of a ring called PM, ring of Motivic periods, which is basically all such possible IM modulo some relation, some linear algebra relation that encodes relations between these things. This ring was equipped with a map C, in fact, into the subring of periods, and per of IM is I, and retrieves the number we started off with. And I explained that conjecturally, very, very difficult and very deep conjecture, conjecturally we can just put a little n with impunity on any period integral. In other words, IM is uniquely determined by I. And as I explained, if you knew this conjecture, you would immediately prove some very, very difficult transcendence results in transcendental number theory, which are very much out of reach. So this is a very deep and difficult conjecture. I didn't explain why PM is a ring. But very briefly, it's sort of the obvious thing. Let me just define it on the level of these symbols. If I had two matrix coefficients like this, and I want to multiply them together, then in my category we have tensor products. So I can simply form the tensor product object. And define this to be the product. And with this definition, the map per will be a homomorphism. Okay, so let's do an example. I didn't say much about relative cohomology, so it's perhaps time to do an example, very standard example. So I'm going to take x to be p1 minus 0 infinity, and y to be 2 points, where a I'm going to take to be a rational number bigger than 1. So it looks like this. And then I'm going to take relative to 1a. What's the de Rham cohomology? I didn't explain how to compute this, but I said vaguely it's sort of differential forms on x which somehow vanish along y. So to make sense of that, you need to use what's called a mapping cone construction. It's very basic, but I don't have much time to explain that. But I think you'll agree that the form dx over x is certainly a closed differential form on x. But there's one more, which is dx. Now dx, if we were to view it just on x, it would be exact. Okay, so it would be trivial. But we're doing relative cohomology here. The point is that it's not d of a function which vanishes at both 1 and a. Because x does not vanish at 1 and a, or rather the value of x at a is not equal to the value of x at 1. And so in fact dx as a relative cohomology class is non-trivial. And I'm going to normalize it by multiplying by 1 over a minus 1. So you have taken on trust that this thing is two-dimensional. But in homology, I think you will agree that the relative homology, which is just chains which now have a boundary, there are two obvious chains. There's the chain, the closed chain gamma, which loops around 0. There's also an obvious chain that goes from 1 to a. And its boundary, so the boundary of gamma is 0, but the boundary of this chain sigma is contained in the points of y. So this is q of sigma direct sum q of gamma, and indeed these spaces have the same dimension as expected. Then the period matrix in this basis is the integral of all the forms sigma dx of x, integral gamma dx x. So the integral dx from 1 to a, well, I've normalized it so that it's 1 deliberately. This integral of a closed form around a loop by the residue theorem, it's just the residue at 0 which vanishes here. Here, likewise, by the residue theorem, we get 2 pi I. And the integral from 1 to a of dx over x is log a. Okay, and so this means that we can define the Motivic version of log to be h1xy, which is basically the data of these two vector spaces and this matrix, essentially all this data, but without a fixed choice of basis. And the data of the distinguished element, which sits here, so sigma and omega, modulo some equivalence. So that's the Motivic logarithm, and I hope you'll be convinced that you can just play this game with anything. Okay, so next thing I need to do is I want to define a Motivic Galois group and how it acts on these things. So now I need to do something slightly weird, which are what I like to call de Rham periods. It's not the best name, to be honest. So we can play exactly the same game here, but instead replace the chain of integration with something else. So what are Durand periods? Well, they are matrix coefficients of the form an object M, such as this one here, but now instead of taking a chain of integration, I'm now going to take F to be the dual of a Durand class. So this is weird. This would be the analog of an integral of a differential form against a vector field, or the dual of a differential form. Okay, something a bit non-standard. And we put Durand in the superscript to remind ourselves that this F here is not a homology class. It's the dual of it's a dual differential form. And here the symbols are taken modulo bilinearity and the functoriality relation I defined yesterday. And so we can cook up Durand periods in the same manner. So they are essentially Durand cohomology in some degree of some pairs of algebraic varieties with the data of a differential form and a dual differential form. So they generate a ring again, and this time we call it PDR, P Durand. So classically, you wouldn't normally consider such a thing, but in this context, it's entirely natural to think about Durand periods. So they don't have a period map. Just as a remark, instead they have something called a single value period map. Which in this case will land in the real numbers. In order to set this up properly, I needed to make my category H a little bit richer and include the data of complex conjugation, which I haven't done because I want to keep things simple. So this is just a remark. Those of you who know this, just point out that the single value period always exists for all Durand periods, okay? There's no projection here or anything like that. The single value period works for any Durand periods of any pair of algebraic varieties over Q. This is unconditional. Right, so now we can set up the coaction. So first we define a Hopf algebra structure on PDR. The key ingredient is a coproduct and this is something we really do not see for integrals. It's something completely new. So the formula is very simple. The co-product of a Durand period is sum where E1 up to En is a basis, any basis of M Durand. So M, I remind you, is a triple of two vector spaces and a comparison. We take the Durand component, that's a finite dimensional vector space, and we write down any choice of basis, doesn't matter which, and you can write this finite sum where the EIs are the basis you've chosen and the EI duals are the dual basis. I forgot to say, I think I said this earlier, but here we're working over Q. For purposes of this like mini course, X and Y are defined over Q. I think I may have forgotten to say that. this morning. Okay, so this also has an antipode. This is a coproduct. We also have something called an antipode, which I'll just give you the formula briefly because it's been used quite a bit recently in physics. And the antipode takes Durand period and maps it to, it just switches the arguments f and omega. But to do that, you replace m with its dual object. So this category has duals. It's just what do you think the definition is? So that's just a parenthesis. So with this data of a coproduct and antipode which satisfies a certain number of axioms, PDR becomes a commutative Hopf algebra. So I'm not going to give you the full definition. It's quite lengthy, but it's a Hopf algebra is essentially the functions on a group. So on a group, you have a multiplication law, and on its functions, you have, so that's a map from G cross G to G, you have a group. And so on the functions on a group, you're going to get a map the other way. And it satisfies a bunch of properties. And that's exactly what a coproduct does. It's the formalization of what it means, of the structure on the functions of a group, which comes from the existence of a group law. And in fact, the converse is true. So given a commutative Hopf algebra, we can get a group back. So they're really the same thing. So technically, the way one does this, the notation in algebraic geometry is to say G Durand is called spec PDR. And it's what's called an affine group scheme. And it's one of many possible definitions of a Durand Motivic Galois group. Okay, so this is, I don't want to spend too much time on this, but the easiest thing, if you've never seen this before, is just to think of the points of this group. So I'm going to take R points where R is any commutative. I'm going to take any commutative Q algebra. You could take Q. If you've never seen this before, I recommend just taking C. Okay, so this is a scheme. Scheme is badly translated in English. It means a template. Scheme is just a terrible word in English. I don't know why that stuck, but it's really a template. So it tells you how to find. So if this would think of something like SL2. Okay, so SL2, you can look at the complex points, the complex group SL2 of C. You can look at the real points SL2 of R. You look at the rational points SL2 of Q. So all those things at the same time is the scheme. It's the group scheme. It's a template which enables you to reconstruct all those different groups abstractly from something. So here the group is all those things I mentioned, but let's just take R equals C, for example, and we're going to get a good old matrix group over C. If you're more advanced and you're more familiar with this, you can change C with any commutative Q algebra, and we'll get an infinite set of groups. But that's just a detail. What we do then is, what is GDR? So let's, in our heads, let's put C. Complex points of this group is just the homomorphisms of Q algebras from this ring PDR into R to C. So that's that's a set. It's all the maps from this ring to C. And what does this coproduct do for us? It turns this into a group, an actual group. let me write it down now. Yeah. So the product, so if you have, we have the co-product. So what is an element of the group is just a map from PDR to R. Okay, it's just the data for every Durand period, I assign a number. Okay, that's what an element of the group is. So given two such elements, G and H, I can apply G to this and H to that. When I compose with this co-product, then we define that to be GH. Right? So GH of an element here, so GH, an element Xi, is G, if you like, multiply G of H of delta. Okay, this is kind of formal, but that's what it is. Okay, so we get a group out of PDR. And then from this, we can get a co-action. So this group is going to act on Motivic periods. Here's the co-action formula, and I know many of you have used this, so I guess what might be novel is the fact that this is completely general and not specific to polylogs or multiple zetas or anything like that. So it's just exactly the same formula as before. So again, we sum over a basis of M Durand, an EI dual basis. So we get a co-action of, so we say that P Durand acts on Pm. And this, these things satisfy a bunch of properties, including co-associativity, which says that if I apply the co-action once and then apply it again on the left factor, that's the same thing as if I apply the co-action and then apply the co-product on the right factor. Okay, so now I said that a Hopf algebra is the same thing as a group. Co-product is dual to the group law. Co-action is dual to a group action. So so the co-action delta M is the same thing as a group action. PDR cross PM. And so how does an element take a complex point of this group, an R point of this group? So this is G is a homomorphism. Q algebras, PDR to R. And how does it act on a Motivic period Xi? Well, we first compute the coaction. Sorry, I've written it. So how do we compute the action? So the action of G on a Motivic period Xi is, well, it's the only thing it could be. You compute the coaction, which puts you in PM tensor PDR, and then you apply G. And G just sends all elements here to some numbers. Okay, so time to do an example. Actually, sorry, I'll leave that. Leave that. So I agree that this feels very formal. It feels like nothing's happening. It's sort of hidden under the bonnet. There's some quite difficult theorems, and the fact that this is going to give an actual Galois theory with all the theorems you know, it uses a lot of Tanakian category theory, which is not trivial. Yes? Yes. Well, that's true sort of any Hopf algebra, a general fact. So if you multiply things together, they get more complicated, right? You take two simple things. I take two prime numbers, 5 and 7, and I multiply them, and I get a composite number. It's much more complicated than it was before. And the Hopf algebra is the opposite. You take the dual of multiplication, the co-product, often called co-multiplication, breaks up something into simpler pieces. So if I co-multiply, so that's by definition it's going to break it into its constituent parts because it's dual to multiplication. It's a general fact about Hopf algebras. They never do. So that's one of the key theorems that's baked into this from the very beginning, is that the cohomology is finite dimensional. And that's a super powerful result. So if I get time to do the Mellin case, that's going to give some incredibly strong constraints on everything. So it's true that there are circumstances when we want to put M to be something infinite. But in that case, it's always a limit of finite dimensional things. So yeah, it's important that it's finite dimensional. Okay, so let's do an example. So we had Motivic version of 2 pi I. Yesterday, so it's exactly this picture I've just unfortunately erased. So gamma was the loop around 0. And then we can form L de Rham, which is the only thing it could be. So this group is of rank 1, I remind you. So H1. We saw that yesterday, it's rank 1. And so we want a dual differential form, a dual of element here. There's nothing we can do except just take the dual of this basis element. That's the only sensible definition of a de Rham period associated to this geometry. And when we apply this formula, so n, as we were just discussing, n is the rank of this, it's 1. So we're going to sum over one term in this coaction formula. And so we're going to get the only thing we could, which is LDR, LM tensor LDR, a single term in the formula. And what does that mean? That means how do I act on LM by an element of this Galois group? Well, it just, by the formula at the bottom here, it just acts on this LDR here. So it gives us LM, and an element of the group, by definition, is something which sends a de Rham period to a number. So let's call that lambda G. G in GDR R. G of LDR, by definition, that's what the group elements are, they're maps that assign numbers to de Rham periods. It is something called lambda G, something in R. And so the group is going to take Motivic 2 pi I and multiply it by lambda G. And because it's a group, lambda G is going to have to be invertible in R. Okay, so we've computed the Motivic-Galois group action on 2 pi I. And all it does is it scales it by some non-trivial rational number in R, if we're working over R. Well, it's in R. I mean, that's what I meant to say. It's in R. But if R is Q, it's rational, by definition. Okay, so what we get is really a character LGDR to what's called, in mathematics, the multiplicative group, G lambda G. It's a character. Okay, the next example was the Motivic logarithm. We have it up there. So log MA now has rank 2. Look at the cohomology group here is two-dimensional. So we're going to expect 2 terms in our co-action formula. And it's a good exercise. You write down, we have the Durham cohomology here. That's a basis. We take the dual basis, we plug it into the formula, and you get 2 terms in the formula. And you recognize the first term, it's going to give back exactly this. And the second term in the formula is going to give 1 tensor something new, which we call log Durham A. And log Durham A is whatever comes out of the formula, which is this thing. So this is, you just give a name to the term that pops out of the coaction formula. So that is the coaction of the logarithm. And it has 2 terms as expected because this has rank 2. Okay, so now this is kind of clunky to compute this formula all the time. Let me give you a very quick and intuitive way to guess this formula without doing any calculation. So what you can do is you can form the period matrix, but now I'm going to replace everything in the period matrix with Motivic periods. Okay, so that's a bit of an abstraction, but now we're more familiar with Motivic periods. We're just going to put little superscript m's on everything in this period matrix. And packaged like this, the group action corresponding to this is super simple. I can act on all of these Motivic periods by an element of my group. And in matrix form, it's going to take a very, very simple form. It's going to be just multiplication on the right by a matrix. I call this nu GA, and then this is lambda G that we had before. So nu GA equals the value that G takes on log Durham of A. So it's worth sitting down and thinking about this. This is just some, the standard dictionary between algebraic groups and their functions. Okay, so this coaction formula is completely equivalent to this formula. You have to sit down and work it out. So what it's saying is that the Motivic-Galois group on the period matrix is just basically changing Durham basis. This is the change of basis formula. So that gives you a very quick and easy way to figure out what the group action, Motivic-Galois group action should be, and from that you can read off what the coaction is. So let's just do one final example of the elliptic curve. I know this has caused a lot of confusion in the literature. Of course, you can sit down. I wrote down the cohomology yesterday. You can write down a basis, write down a dual basis, and plug everything into this formula. But if you're willing to take this more sophisticated point of view, we can just write it down. So E prime is the punctured elliptic curve. Smooth elliptic curve over Q that we saw yesterday. And we had the period matrix, which I'm now going to promote to a Motivic period matrix. And we had eta alpha to the m, eta beta to the omega alpha. That's my Motivic period matrix, and what these are. So, for example, omega alpha beta was the integral of x over y over alpha or beta, and the period eta m alpha or beta is the integral of alpha beta of the differential of the second kind. Okay, so this is the standard period matrix of an elliptic curve, which is centuries old, but I've just promoted everything to Motivic versions, which we now know how to do. So how does the group act on this? Well, if I act on this period matrix, it's just going to multiply on the right by a matrix. AG is in GL2R. Okay, so that's how the Motivic-Galois group acts on these Motivic periods. And we had this Legendre relation. So there's a Legendre relation, which is also true on the Motivic level, which is that the determinant of this Lm, and that implies that the determinant Ag is lambg. How does the Galois group act on elliptic integrals? Well, it acts by sending one to linear combinations of the others in an unconstrained way, except that the determinant of the matrix transformation should act in the same way that it acts on pi. Okay, wow, I'm very, very far behind. So that's it for the setup, and I hope I've tried to convey that it's not so hard, finally, to set up a completely unconditional Galois theory of periods, and that you can compute, you can do examples, and it tells you give you new insights into the problem you're working on. I had intended to say something about multiple zetas to show that these formulae are really doing something highly non-trivial. I had also intended to say something about Mellin integrals. There's clearly no way that's going to be possible. There will be notes from the Trieste course, which is on which this is a bowdlerized version of. The question now is, what do you want me to do? Shall I go over MZVs, or do you want me to say something more recent about Mellin? Sorry, yeah, let's vote. Okay, MZVs, hands up for MZVs. 1, 2, 3, 4, 5, 6. Okay, hands up for Mellin. Okay, Mellins have it. Okay, so what I wanted to say, okay, so I'll assume, since there are many physicists here, that you know the MZV picture well. So what I'd recommend, there is software you can download. So Oliver Schnetz has some code based on earlier code called hyperlog procedures. And I'll just say in 2 words that the best way to get a real feeling for this is to play with it. There are things called Motivic multiple zetas, they're Durand versions, and you can put this in the computer and it will compute the coaction for you, and it will respect every possible algebraic relation that you can think of, and it's really miraculous. So you have to see it with your own eyes, and then it's kind of a revelation that this very formal structure does anything at all. It's in fact incredibly constraining. Just mention one thing. There is what you can do in this setting is you can, in great generality, you can look at the Lie algebra of the Durham Motivic-Galois group, and it acts via differentiation. It acts via differential operators. So in particular, you get, so you can, this means that you can differentiate a motivic period with respect to something. And in the MZV context, there are certain differential operators, delta 2n plus 1, which correspond to differentiating with respect to the zeta 2n plus 1. This seems a very, very weird thing to do in mathematics, like differentiating an expression with respect to a number, but it works. And it's super powerful. And what I want to do is to copy Sam's brilliant exercise and come up with my own annoying exercise. For those of you who know this theory, annoying exercise, find in the literature. Oh, yeah. It was great. So I thought I'd steal it. Find in the literature a sequence of MZVs. So there are loads of problems in mathematics that have nothing to do with algebraic geometry that produce a sequence of multiple zeta values coming from PDEs, coming from physics, coming from all sorts of different parts of mathematics. So they've got nothing to do with this a priori, or more generally periods. So take that sequence, compute these differential operators, on them, take the sequence of numbers and compute the differential operators. I guarantee you that will generate relations between these numbers. That will produce for you some kind of motivic differential equation. I've never seen it not work. You get periods which are algebraically independent, that don't talk to each other at all, but which somehow, when you differentiate one, it relates them in some very subtle way. And then the third part of the paper is the third part of the exercise is to write a paper, because this will give a connection between your problem in PDEs or whatever and Motivic-Galois theory. And in general, I have no idea why this works, but it always works. Okay. I guess one of the first adopters of this would be the bootstrap program in n equals 4 super Yang-Mills, where this is now baked into the program. Enables you to predict amplitudes at higher order from lower order, because they talk to each other through these operators. Okay, so Mellin. I have 15 minutes, okay. So I'm going to have to be very, sorry? 1.5 hours, not 1.25. Okay, cool, okay. No, I have 15 minutes. 9:30. My goodness. Okay, well, we're here now, so I can slow down. I'm really sorry, it's like this shift of 15 minutes is just too confusing for me. Okay, so this is joint work with Clément Dupont, Javier Frezan, Mathieu Tafuskovich. So we're going to start with a Mellin integral. Okay, so there's a lot to say here, but let me be a bit sketchy. So it's the same as before. We're going to take omega, a regular n form on smooth variety X. I'm going to just be over Q now to make life. So this is an algebraic variety, system of polynomial equations. It's got to be smooth. Take our n form. We have a chain of integration, same as before. Sigma is contained in the complex points, which is a smooth manifold. Chain of dimension n. So far, so familiar. It can have a boundary as well. That's okay. Same as before. And y is over q. Y is fine over q. But the new data is these f's. So f is this tuple fr, which is a map from X to the multiplicative group. Let me not write that. Let's just P1 minus 0 infinity the R. So the FIs are just polynomial functions on X, okay? They can be any polynomial functions. Okay, so this integral is going to define a meromorphic function of S1 up to SR. And it's going to converge when the real part of the SI is sufficiently big. I'm going to assume, let's just assume it converges. I have to be a bit more careful about where F is defined, but let's just say it converges for real part SI bigger than 0. Anyway, so what we're doing in this joint work is to this kind of setup, we can associate a Mellin motive. The word motive is really not good here because there's no even conjectural theory of motives for these types of objects. It's something completely new. But what we do is the Durham and Betty side of this story. So our motive for the time being is again, a triple, some kind of Durham interpretation of the integrand, some Betty interpretation of the chain of integration, and some comparison isomorphism, which encodes the integration pairing. Okay, so what's M Durham? M Durham, it's various different things in different contexts, but it's approximately relative homology group. I'm being very sloppy here because not quite this, but in the general setup would be some kind of relative cohomology group, but with coefficients in some algebraic vector bundle with connection. Some kind of twisted cohomology with integrable connection. So it's twisted cohomology in the physicist sense. So this is a very specific type of algebraic vector bundle. It's really rank 1. So V is OX, and typically nabla is D plus some SI dFi over Fi. So if you're used to string theory, this is very, very much what you're used to thinking about. Though the precise meaning of this is something slightly different from what's in the literature. MBETI is some kind of relative homology with coefficients in some local system, some kind of twisted relative cohomology. And these are finite dimensional vector spaces. With lots of extra structures. They're very interesting. Okay, so let's admit that you can set up some kind of Durham and Betti theory that explains these integrals. We can play the same game. We can set up Motivic versions of the Mellin integral. So what will happen typically is the Motivic version of this integral will be the object M, a Betti class, which is, if you're familiar with the literature, it's what's called a loaded cycle. And then the Durham class will be the data of omega. Maybe I should put Mel here. Some Mellin Motivic period. Yeah, I hope you can believe that you can set this up with the same formalism I described once one has a very good understanding of this. Then you can apply the same coaction formula. And you can play the same game. Because this coaction stuff was just linear algebra. Okay, so straight to some examples. The first example is the beta function. So it's convenient to normalize it this way. So the beta function of S and T with this prefactor is, I've written it a slightly funny way, but you're free to rewrite it how you like. X over 1 minus x. And this integral converges for real S and T bigger than 0. Okay, so you can write down the corresponding cohomology groups. I'm not going to do it. Many of you know what it is, especially if you're from, this would be the string amplitudes in tree level with 4 external particles. And you will know that the rank of this object is 1. The corresponding Mellin object is a rank 1 object. So think of this as an analog of 2 pi I. In the classical world of periods, 2 pi I was a rank 1 object, the cohomology was dimension 1. So beta is like a Mellin version of 2 pi I. Good way to think about it. The next example that's interesting are hypergeometric functions. Not quite. It's really not the hypergeometric function that comes out on the nose. It's something slightly different. curly f a, b, c, y is the beta function b, this is right, times 2f1 but when you do the integral, you don't get the hypergeometric function on the nose, you get this beta function prefactor, so that's very important. So here we have the Gauss formula. X. Okay, so this is a bit more sophisticated because it's a function of a, b, c, but it also depends on a parameter y. That's okay, I claim. So you can imagine that from this cohomology group, from this integral, you can think about how to interpret this as a pairing between some chain or some kind of loaded chain and some differential form, some integrand. When you do that, you compute the cohomology and you get something that's now a rank 2. It should be familiar because the differential equation for the hypergeometric function is a rank 2 system. So the way to think about this is somehow analogous to our elliptic curve example. Elliptic integrals that we looked at. Elliptic integrals. To think of the hypergeometric function as the Mellin or a Mellin analog of elliptic integrals. That's a useful analogy. Since I mentioned it, in this we also have string amplitudes. Yeah. Because I really want to think of this as functions of a, b, c, and the integral, so the period is this integral. It's not the hypergeometric function, it's hypergeometric function times beta. That's what comes out. Well, if I wanted to write the hypergeometric function as not a period, it's a quotient of periods. It's this integral divided by the beta function. It's an integral divided by an integral. Well, beta happens to be group-like, but you might get away with it. But I would strongly advise against doing that in general. And the theory says you take an integral. In all this game, we take an integral, we interpret it as some pairing between some cohomology groups, and we run this machine. And this is what we're doing here. We have an integral, we interpret it, we run the machine. And that gives us a Motivic interpretation of whatever this integral is. And that's this. This guy f, not that. Make sense? Can I say again? Because this is not an integral. This is an integral that's defined where everything in sight is defined algebraically. I don't want to divide. If a, b, c were fixed, is what people often do, then I can this is just a rational number, I can divide by it. But I really want to think of this as a function of a, b, and c. And so I really do not want to divide by this. Because it's going to mess up the coaction, something wrong. Maybe not in this case, but in general, it's going to do something terrible. So this is really as a function a, b, c. I'm just saying that this is what comes out. The integral is this, and the theory gives Motivic versions of integrals. It's just that the name in the literature that people give to it, f21, is not on the nose an integral. It's a quotient of integrals. And that's very wide. There are all sorts of things in mathematics that are people say are periods, but they're actually quotients of periods. Sorry, I can't hear. Why would what, sorry? Oh, right. So yeah, there are two things I can do. I can fix y. Let's do that for today. But I can also do Mellin motives in a family. And then we can also think of y as a variable and view this as a family in the y coordinate. that's perfectly fine as well. Yes. So well, the two stories. I don't have time to go into this, but there are two aspects to a Mellin motive. There's the sort of what I'm talking about here is the sort of global aspect, which sees the differential equations in Y, and it sees all the contiguity identities. Okay, so you have contiguity identities, you have differential equations, and on top of that, you're going to have a Motivic-Galois action, and it's going to be compatible with everything. So that's new. I'm not going to talk about that. What I'm going to talk about is what happens when you Taylor expand in ABC. And then I want to connect that to the previous. Yeah. So I'm just going to say that now. So these are incredibly rich objects because they have all this structure, the contiguity, the differential equations, the expansion in periods. But it's just mind-blowing. So I'm just going to focus on one thing and just to give a hint because we're working on this at the moment and we don't understand everything from it. But I think that the expansion thing is what I want to talk about. But I agree, this is completely fascinating. We get a Motivic-Galois action which is compatible with contiguity and differential equations in Y. And that's pretty cool. You can. You can do that. That's a different story. So you can fix ABC. You can even allow them to become integers, and then some very subtle things happen. Like the rank of this thing can jump, and it can jump up. Okay, so then you can be in big trouble because some very subtle things happen. Okay, so there's a map from this thing. There is a specialization map, and it's given by what's called the base change map in mathematics. That exists unconditionally. But sometimes it gives you no information. So if I write down not beta function but p1 minus 0, then the Mellin object is 0. And when you degenerate at an integer point, it becomes rank 1. So there's no way that you can get something non-trivial from 0. And this is a sort of gripe I have with IBP relations because people do this all the time. And it shows there's something fundamentally that you can't do here. This is a huge topic, a big can of worms, fascinating. I really don't want to go into that here, but yeah, that's on the program. It's very, very interesting. And what happens to these contiguity when you degenerate? Anyway, string amplitudes. Let's just call this. Let's just do a 5 mark points in my notes. So I love this family of integrals. It's absolutely fascinating. So this would be the 5-point function. This is deliberate to write S4 and then S3. 1 minus xy. This family is the 5-point function in string perturbation theory at tree level. So you guys know this. And it's fascinating because it tells you Apéri's proof for the irrationality of zeta2 is contained in this in a fascinating way. And of course, as David mentioned, Feynman integrals in now d equals, let's say, 4 minus 2 epsilon dimensions. And now our Mellin parameter is epsilon. Okay, so this is exactly what we want to be doing. So let's go back to the beta function. I told you it's a rank 1. Yeah. Yeah, so that's what I was just saying now. So if the S are generic, if they degenerate, then bad things happen. But I'm not talking about that today. I'm going to expand in the S's, which is something completely different. So do I have 10 minutes now? Is that? Okay, now I'm behind. Okay, so go back to the beta function. So it's a rank 1. So if we were to apply the coaction formula, like 2 pi I, we would only have one term in the formula. So beta is rank 1. This implies that the coaction formula has no possibility to be anything other than delta of beta is beta tensor something. And so because it's rank 1, there's only one term in the coaction formula. It has to map. In other words, the group multiplies the beta function by something. So I'm just going to give this a name. We're going to call it beta Durand. Okay. And there's a normalization factor. And in everything I say so far, I'm going to now assume L Durand is 1 just to make my life easier. Otherwise, the formula are a bit tricky. So that's the coaction on the beta function. Okay, so now I want to talk about expansion. So to justify this requires a lot of work, but let me assume that I can expand my Mellin integrals around a point, because this is what we want to do for physics applications. For example, the origin. So the integral might not have converged there. Okay, there's work to do. But when everything works, I can expand my f to the s and write it as an exponential of a logarithm. Let me do that here. So I can substitute fi to the si equals exp si log fi, and expand it formally as si to the n over n factorial log to the n fi. And so I'm going to get infinitely many integrals with logs of f's in it. The log of f I can write as an integral. And so I can substitute, instead of log f, I can put integral of dx over x with suitable endpoints. And so I'm going to get a giant integral with a very, very high, I'm going to get a power series in integrals. So you have to trust me, but if you do this carefully, you get an expansion of your Mellin integral. And the coefficients are themselves integrals, and they're periods. Okay, so these are periods, the formal power series in periods. Ordinary bog standard periods. There's no Mellin here. It's just a connection between the world of Mellin integrals and ordinary periods. And so I'm going to do the obvious now and make everything Motivic, because that's what we've been doing these days. So you can lift this with considerable care, lift to a Motivic expansion. So let me call this expansion of IM. So this is the Mellin Motivic period, whatever that means. We'll have an expansion now in Motivic periods. This is a formal power series in Motivic periods. What's interesting here is that these are periods of completely different geometry, completely different motives, and they talk to each other through the fact that they are packaged they live in the same Mellin integral. This gives a way for periods of completely different types to communicate with each other, because they arise as expansion of the same Mellin integral. And this is quite fun. Also, this is what has been going on in physics for many years, expanding, like in the work of Ollie and string theory, expanding string amplitudes and formally identifying the expansion coefficients and putting as motivic periods and putting superscript m's. So here's an example. If we do this to the beta function, we can expand the beta function. I'm going to put expand this, and you get the motivic version of the very classical formula for the beta function. -1 to the n minus 1. Theta, now I put an m because it's motivic period here now. And so that's what you would expect. You know, the classical beta function expands into zeta, so somehow the Motivic Mellin beta function should expand in terms of motivic zetas. Correct. Oh, did I miss something in my formula? No, I think this is correct. Correct. Yeah, so a motivic zeta 2, this was actually in my notes, but I didn't have time to. This is 2 pi motivic squared minus 1 over 24.
Okay.
This is due to Euler. Yeah. And the rest, yeah. So any identity which you know is true when you put the superscript m's. And conjecturally, that's true for any periods. You can do this with confidence in the m's. Okay, so coaction theorem. This is in progress with my co-authors. And it basically says that the motivic Galois action or the motivic coaction commutes with expansion. Motivic coaction, let's say. This is very surprising. It's inspired by experimental work of Ruth and co-authors some years ago in the physics context. But very soon we hope to have a completely rigorous, well, we have a complete proof, and it should be available at some point, I hope. So here's the theorem, again in slightly cartoonish form. Let IM SR be a motivic Mellin period with expansion the one I wrote down, let me just write it again. So it's an expansion in motivic period in periods. Some n, an motivic, and R, a formal power series in motivic periods. Then the expansion commutes. So if I do expansion of the motivic Mellin coaction on this thing, so this is a finite, because the Mellin object has finite rank, there's a finite sum. You sum over a basis of the Mellin object, so the sum over the twisted cohomology, sum over a basis of the twisted cohomology, and you get something. And the theorem states that that's the same thing as if you computed the ordinary motivic coaction term by term on the expansion. So in other words, the coaction in the Mellin world is consistent with the coaction in the world of periods. You might think, yeah, sure, of course. But actually, it's pretty surprising because, yeah, I'm out of time. Okay, so let me just conclude with one example. Let me just do the beta function wrap up. That's the theorem that will be forthcoming. So example, let's do it here. Save me some time. So we have the beta function here. I had a formula that it's somewhere, some zeta values when you expand it. And so this formula is equivalent by the theorem to the formula delta Motivic theta n equals delta Motivic n tensor 1 plus 1 tensor zeta Durham n. So of course here I'm setting L Durham equal 1 to make my life easier. And so the fact that the beta function is rank 1 encodes infinitely many coaction formulae, the zeta values, which are non-trivial. And it explains, for me, for the first time, why the zeta values all have the same coaction formula. Uniformly, they're completely different weights, they're completely different motives, they have nothing to do with each other. The fact that they both live inside the beta function tells us they have to transform in the same way as each other with the Motivic gamma group. So final comment, that the fact that the Mellin motive is finite dimensional implies, via this theorem, that the expansion coefficients always satisfy Motivic differential equations. With respect to these exotic differential operators and their generalizations. So for me, it goes some way to explaining why often in mathematics where we see sequences of MZVs, we find this recursive structure that's very mysterious. I don't know why that's true, but at least when it comes from a Mellin integral, then that's exactly what we expect to see.